Hi everyone, my name is Omar Boufous. I'm a PhD student at Orange, affiliated with the University of Avignon. I'm going to be presenting an algorithm for learning equality equilibrium, which is based on regret minimization. And this work was done with Rachid El-Azouzi, Mikael, Touati, Eitan, Altman, and Mustapha Bouhtou. And from the title, you understand that we're going to be discussing correlated equilibria, which are a generalization of Nash equilibria that were defined in the 70s by Omar. And in our case, we're going to be looking at correlated equilibria and finite strategy games, even if the same solution concept exists also for extensive games and even infinite games. In this work, we're going to be focusing on finite non-cooperative games. As you may know, correlated equilibria are interesting for many reasons. One of them is that by definition, they may lead to better outcomes than Nash equilibria. By better, I mean more optimal or fair distribution of payoffs among the players, as we will see in one of the examples later. And this is relevant, especially for some applications in engineering, for example, in which the performance of the system is particularly important. The other important property of correlated equilibria is that, unlike Nash equilibria, a correlated equilibrium can be expressed as a linear program solved in polynomial time, and this can be done when all the game parameters are known. So it's pretty straightforward to find a correlated equilibrium point in this way. But this requires information about the game, and this information is not always available in centralized fashion. So, in some cases, when we have limited knowledge about the game, we are interested in learning methods, and there exist several learning techniques for converging towards collective equilibria that operate under different assumptions. So, for defining collective equilibria, we need to define the game model, which is made up of three elements. The first one being the set of players. We didn't have an action space AI for each player I and utility function defined for each player as well. Now we can state the definition of collective equilibrium probability distribution for the game G, which is a joint probability distribution over action profiles which satisfies the equation 1. Now what the equation or the inequalities in 1 say is that P star is a collective equilibrium probability distribution if for every player and every pair of actions, AI and AI prime, the expected utility obtained under P star is greater than the one the player obtains after unilaterally deviating from AI to AI prime. So the stability condition or the equilibrium condition here is defined in a very similar way as what is commonly done with Nash equilibria with respect to unilateral deviations in this case to pure actions. As an example, consider the two-player matrix game in Table 1. This game is called the traffic intersection game because it can be seen as a model or representation of this strategic interaction where we've got two players, which are actually two vehicles that are at an intersection, and each one of them can either cross or go. Oh, sorry, can either cross or wait at the intersection, and if they both choose to cross at the same time, they collide and get penalized. That's why they get a negative payoff of -1. Now, this game is actually a variant of the chicken game, and for this particular utility matrix, we have three Nash equilibria. Two of them are pure, and one is a mixed equilibrium point. And each one of these equilibrium points yields a vector of payoffs that is represented on this plot. And as you can see, the mixed Nash equilibrium payoff vector 0, 0 is not efficient, while the other two pure Nash equilibria are not fair because for each one of them, a player gets one while the other one gets zero. So it's quite an imbalanced situation. Now, if we look at the achievable payoffs in this game, and they are represented in the blue area, and these points are obtained with all the possible distributions over action profiles. Now, what we can see is that there are potentially more interesting outcomes that are reachable in this game. For instance, I highlighted this point in green, the point 1.5 and 1.5, obtained with this probability distribution, for which the profiles wait go and go wait are played with probability 1.5 each. And now this probability distribution over action profiles is a correct equilibrium probability distribution that satisfies the definition we saw earlier. And one thing about this probability distribution is that It cannot be achieved with totally independent mixed strategies, as it was the case with Nash equilibrium strategies. However, if we introduce correlation, it is possible to randomize equally in this way over these two action profiles. And this equilibrium situation can be better understood and even implemented in this game with traffic lights. The role is to correlate or synchronize the decisions of the players, make sure that whenever one crosses, the other one awaits, and vice versa. In practice, this is what is actually done with traffic signals, sending information to every player. And in road traffic, um, the information green is associated with the action go, and red is associated with the action wait. Now, this probability distribution is a single example of a correlated equilibrium probability distribution, and the black area here represents the pair of pairs of all correlated equilibrium distributions for this game, which naturally include the three Nash equilibria. And as I mentioned, it's pretty straightforward to obtain this set when the game is known. So we know the players, we know their action sets, and we know the utility functions. But this is rarely the case. And in this study, we are dealing with the learning problem in order to reach a correlated equilibrium uh, when we have a limited knowledge about the game. And so, in this context, the game G is played repeatedly, and as a consequence, it generates a history of play, and we are interested in the trajectory of the empirical distribution of our action profiles. We're going to assume two things. The first one is that the player only knows his utility function, and the second assumption is that the history of play is known to everyone. Now, this all comes down to the question of how can we play the game repeatedly so that the empirical distribution converges to a correlated equilibrium probability distribution. And as you may have noticed, we are faced with a multi-agent learning problem where we have multiple players interacting with the same game, so performing actions and getting as a feedback the utility. And through this repeated interaction with the game, we're hoping to converge towards a correct equilibrium point. Now, this question of how we can achieve this is not new. We're not the first one uh, to um, to try to answer this question. There exist several methods in the literature. The most well-known algorithm is called regret matching, which guarantees the convergence of the empirical distribution to the set of correct equilibria. The second algorithm is a method based on reinforcement learning, which proposes a feature to select a correct equilibrium that satisfies certain conditions, but this requires each player to know not only his utility function and the actions of the others, but also it requires knowledge about the utility of the other players. Another algorithm proposes a method which guarantees convergence to the social welfare maximizing point, which also requires some knowledge about the set of correlated equilibria. The last example is a reference to a paper in which a method for learning correlated equilibrium for a special class of games is presented. And so in this work, our goal is to design a learning rule to converge towards the correct equilibrium point without any prior knowledge of the game. So in this situation, a common approach consists in using the notion of regret, which is pretty common in online learning. And the regret is a quantity that measures the past performance of actions after some sequences of moves. So the regret is defined for each player, and for each pair of actions, G or J and K, and it is defined as the pair of difference between what a player obtained during T sequences of play with what he could have obtained if he played K instead of J. The important thing about regret is that if we play what we call regret minimizing strategies, so that means strategies that are or that imply uh, that in the limit the regret is tends to zero. The empirical probability distribution converges to the set of quadratic equilibria. So as an example, if we apply such a procedure in a game like this one, this is the evolution of the empirical probability distribution we obtain. So all the regrets are minimized, and the trajectory keeps hovering over the set of quadratic equilibrium distributions. In particular, it does not seem to converge towards a point. And in this work, uh, we propose a new dynamic we call CPRM, which stabilizes the empirical distribution. For this purpose, in our algorithm, the players are characterized by a mood. So a player can either be synchronous or asynchronous, and depending on his mood, the player will play differently. More precisely, asynchronous players are going to be implementing a regret minimizing strategy, while the synchronous players play the action or the component of the action profile drawn from the empirical distribution at time t. So in the long run, what we expect is that players are going to be playing the action profile drawn according to the empirical distribution, which will, in the long run, stabilize the play at an equilibrium point. So in the algorithm, the modes evolve according to these probabilities of transition. The idea is that the lower the regrets, the higher um, the probability to transition from asynchronous to synchronous. And the probabilities of transitioning depend obviously on the regrets and also on the perturbation parameter epsilon. What we show is that the stochastic process that is induced by this learning dynamic is a perturbed Markov chain, and we are still working on the proof of convergence and the long run behavior of the chain. The motivation is that for the perturbed homogeneous Markov chains, the process converges towards stochastically stable states as the perturbation term tends to zero. So when we apply our algorithm to the previous matrix game, which has two Nash equilibria shown in red on the figure, we observe that the trajectory of the payoffs seems to converge to a point in the neighborhood of the convex hull of Nash equilibria. Now, if we look at the trajectory of the empirical distribution, our algorithm is able to stabilize it, which is not the case for regret matching or other regret minimizing strategies. I also have the evolution of regrets, and here again, CPRM is able to stabilize the dynamic, while the other two algorithms we observe uh, an evolution of regrets that are decreasing, which is what we expect from these type of learning procedures. So the last experiment we conduct is on a time-varying game, because in the initial setting we assume that the game played does not change um, with time, but we propose an adaptive version of a CPRM that is able to deal with these changes in the game. In particular, um, if we have new players that are joining the game or already existing players that leave the game, and we are able to observe the same convergent behavior as we're able to stabilize the empirical distributions for each one of these games, even if we have players leaving or new players joining. And this is a very interesting property in many settings in networks where the number of players changes. So to conclude, we can say that we introduced a new learning rule, CPRM, um, for quality equilibria in finite non-cooperative games, and we obtained encouraging simulation results showing convergence towards an equilibrium point. We also present an adaptive version that deals with changes in the game, and we still have to conduct a detailed analysis of the convergence of the process. So yeah, thank you for your attention. If you have any questions, feel free to ask.